welcome. In this lecture, I'm going to talk about another kind of function not being continuous at an x value a, so not being continuous. And this is going to be removable discontinuity. And these are nice because you can actually turn these functions into continuous functions. So let's look at an example. So I have x. So this is my x-axis. This is my y-axis. My function here is going to look like, so it's going to go like this, and it's going to go like this, and it's going to go like this, and then it's going to go like here. Okay, so what's happening here? So this is my function y equals f of x. And what's happening with my function y equals f of x? So at the value, this will be the value x equals 2, right? This is the function f of x is going to equal, so this you might be able to kind of tell from the shape. So this is x cubed, as long as I'm not at my x equals 2. So this is for, so here we're not at x equals 2. And then if I'm at x equals 2, I'm just going to assign it the value 1 for some reason. Maybe there's a circumstance at a particular quantity, the cost is different for some reason. I don't know. There can be things that can happen at a particular value. That's actually not a completely absurd thing to happen. So then we have, what's the problem here? Well, in this circumstance, if I'm going to take the limit as x approaches 2 from the left-hand side, okay, so I'm going to have the limit as x approaches 2 from the left-hand side of f of x, right, and I'm going to look at the limit just kind of like we did before. It's defined at x equals 2, so that part's not a problem. And then we look at the right-hand side. So as we look at values of x that are greater than 2, well, for both of these, because we don't actually care when we're taking limits at what happens at the particular value, we're actually okay. We can just plug these in. We can use these functions because we don't care, right, about what happens at that particular value. So we have here, we just plug in 2 in both of these circumstances, and so we get 8, so these are equal. Okay, so in this regard, we're okay. Okay, so that limit does exist. However, remember that we additionally needed that this value should be the same thing as what we get when we actually plugged in f of 2, right? But this does not, these are both 8, right? So we have 8 as an output, and 8 is an output when we take those limits. However, when I get this, so f of 2 is actually equal to 1, right, coming from here. But the problem with that is that does not equal this 8. Okay, so I have 8 and 8, those match up, but they do not match up with what actually happened if I put that value x equals 2 into the function. Okay, so when we have a circumstance like this, the first thing that we know is that f is not continuous at x equals 2. So the first part of it is that f is not continuous, so f is not continuous at, when we put in this value of x equals 2. Okay? And so it's not continuous overall, so f is not continuous. Right? But something bigger happens, which is we know because the problem was not with the 2 limits, but was with actually sticking the value x equals 2 into the function f, then what we actually know is that what we have is a removable discontinuity. Okay? And we have, so, and the circumstance is that f has a removable discontinuity has a removable discontinuity at x equals 2. Okay, so removable discontinuity, you could actually have that the left-hand limit, so where the values of x are less than our a, which is 2 in this circumstance, and the right-hand limit, where our values of x are greater than a, which in this circumstance is 2, those could actually be the same as they were here. But what makes it a removable discontinuity is that the value of f at 2 is actually different, so it's not that same value 8. Okay? So, I hope that made some sense, and I will see you in the next lecture.